Yes, Riddhi, am I audible to you?
Yes, ma'am.
All right. So, good morning, Riddhi. In the last
Good
class,
morning,
we
ma'am.
started with the magnetic field and all. So, Biot-Savart law we did,
Yeah,
and
we
we
finished it.
discussed that Biot-Savart law B is equal to mu naught I dl sine
Yeah,
theta by r square. And direction part was left. We didn't discuss the direction, Riddhi. Till here, we have only
we
stopped.
did till the vector form. Yeah.
Vector form. Yes, let's come to the direction. Now, Riddhi, for the direction, uh, you also do it along, okay? So that you get the two methods. For the straight wires, I'll be teaching you two methods, okay? Both the methods are applicable on through both the methods will lead you towards the same answer. So it's just that whichever method you find it convenient, you use that. Other method you can leave. Okay, because
Okay.
nobody in the exam will ask you to solve a question using a particular method. These are fixed right hand rule, left hand rule, whatever you can say. Okay, so see, there are various rules that are present. Left hand rule, Fleming's left hand rule, you must have heard. That's a very famous rule which we
Yeah.
use in the lower classes and all. So see, what we'll do, Riddhi, throughout our physics of 12th, wherever direction is required, we'll be just using our right hand. That's it. So that it doesn't
Okay.
confuse you. Because if you have somewhere you have the left hand getting used, somewhere you have the right hand, so you'll be very confused which one to use, right? So be very clear, we'll be just talking about the right hand. So you will also use
Okay.
your right hand. So in the exam, don't ever be confused. You know, you have to start with the right hand. It will be different. Sometimes thumb will be representing something else. The index finger will be representing something else. That's a different thing. Now here for a straight wire, using the Biot-Savart law, you will get the magnitude. But for the direction, you will require the right hand. So what will you do? For the first one, wherever the current is moving, let's say the current is moving upwards like this. What you do, you put your thumb across the direction of current. Wherever like this. See, thumb will go up
Yeah.
because current is going up. Wherever you have the current present, put your thumb in that direction. That will give you the
Okay.
direction of the current. Means direction of current will be given. You will just put your thumb according to that. Now see, Riddhi, if this is the thumb, my A point, let's talk about this A point. A point is situated towards the left side. Your
Yeah.
left may be something else. In the camera, it gets reversed. So just check.
Yeah.
So if this is it, my left is this. This is the A point here. Okay. Now see, just see at this point A, where are the fingers going when you are curling them? Like, see, if I look, they are coming towards me and then going.
Yeah.
So this is outwards. Okay.
Yeah.
So
A is
this will be,
outwards.
this direction will be outwards. Or see, let's say this B point. If this is the direction of the current, see, now the point is B is on the right side. So if I
Yeah.
take this, now see, when I curl it here at this B point, fingers are pointing into the screen inwards. So this will
Yeah.
be the direction. Now see, I personally do not prefer this method because sometimes it becomes confusing. Is the finger curling in or curling out? But if you're comfortable with it, you can use it with any methods. As I said, you should just get the right answer. And with both of the methods, you will get the answer. This is the first method. Okay. Now let me tell you. Let's discuss few things through this method. Let's say, or let me tell you the second method. Let me brief you with the second method so that whichever method you are comfortable with, you can answer with that. Let's say the current is upwards. Okay, same thing.
Yeah.
Now I should get the same answer. I know this is outwards, this is inwards. So for both the methods, we should get the same answer. This method is quite simple. You take your palm, the right hand. Okay, right hand will be used, and you put it along the direction of the current. Wherever the current is moving, you put it along the direction of current. So current is upwards, so our hand will also be upwards. Yes?
Yeah.
Now see, point is situated towards the left. You have to curl the fingers pointing towards the point of calculation. See, if I keep my hand like this, point A is on the left, I'll not be able to curl it. If I keep my hand like this, now I am able to curl it towards the left one. See, where is the thumb pointing? Outwards.
Yeah.
So thumb will directly give the direction, whether it's outwards or inwards. You don't have to analyze.
Okay.
This is how. Or let's look at this V point. Same thing. Not the second method. We'll have the palm facing upwards. Now, if I keep it like this, point B is on the right. So this curling isn't possible, right? We'll have to curl it like this. Thumb is directly pointing inwards. So this is giving the answer inwards. Can you tell me for this A point? This is the direction of current.
So it would be like this.
Yes.
So for A, it would be inwards.
Yes. Very good.
And then for B, it would be outwards, towards you.
A will be inwards and B will be outwards. I'll just tell you one more thing. For inwards, this is the symbol cross.
Yeah.
You can just put a cross also. That is a standard acceptable answer. Symbol. And dot will represent outwards. So you will see, often you will see crosses are made. That means the magnetic field, all the magnetic field is pointing inwards. That is how we see. Okay. See, this was very simple. You had the thumb like, you had the palm like this, curling, pointing inwards. Similarly, like this.
I never knew this method.
Okay. Tell me for this one, this A.
So, okay.
Point is upwards.
So if we're keeping it the direction.
Yes.
I'm confused in this one. Let me
Point is above your palm, above the eye. So,
oh, like this, or no?
see, right hand.
Yeah.
You put it towards the direction of current. Now, current is towards the right.
Yeah.
So we have put our hand towards the right. Now, where is the point A?
Above.
Where do we curl our fingers? To the point?
Towards. Yeah.
So if the point is A, just curl your fingers. Where is your thumb pointing?
Backwards.
Nothing is
So
backward here.
inwards.
Outwards.
Outwards.
Inwards means pointing into the page.
Oh yeah.
Okay.
Outwards.
Okay. Tell me for this B point.
Then like this.
Yes.
And then so then it will be inwards.
Correct. This will be inwards. Try for this, Riddhi. A point here. This is the current.
A would be inwards. Then
A
like
will
this.
be, yes.
Inwards.
See, current is going like this. Point is here. So, and B?
Outwards.
Out. So, got it? Got the direction part for this? Okay. Now, we'll come to the application. That covers the Biot-Savart law. We'll come to its applications. You first write down this part.
I won't write the right hand thumb rule because I'm already aware of it.
You won't?
I won't write the right hand thumb rule part. I'll write the new method.
Both are right hand thumb rule. All these are right hand
thumb rule.
All these are right hand thumb rule only. See, you just have two main rules: right hand rule, left hand rule. Okay. So both of these are right hand thumb rules only. It's just that methods are different. Okay,
I'll write the method too then.
Okay, then you write the method too. But then write the examples from here.
Okay.
Done? Okay. See, cross product, I hope you remember. You're muted, Riddhi.
Yes, ma'am, I remember.
You remember how to write the directions? If I say I cross j, it will give you plus
Like
k cap.
this?
Yes,
Yes.
yes, yes. You remember that clockwise and
Yeah, I
anti-clockwise?
remember.
Okay, great. Then no need to write this then. Many students sometimes forget, so I just put it in the notes. See, this is a question from your NCRT itself. Look, here it says the current, usually we have the current like this along the y-axis and the point is present like this. In this question, the wire is present along the x-axis like this. You have the wire like this. And current is moving towards the positive x-axis with the value 10 amperes. Now in this question, only the figure is drawn and you have to interpret everything from the figure itself. But it's not difficult. See, if current is flowing 10 amperes towards x-axis, it means this is the wire,
Yeah.
right? And see, this is the point P where you have to calculate the magnetic field. So separation between the point P and this wire is given as 10 meters. There's a small element already given in the question, delta L, that is 0.01 meter. And since both are axes, y and x, it's obvious whether it's mentioned or not, that angle will be 90 degrees. All the three axes are
So it will be
perpendicular to.
Biot-Savart's law.
We'll use Biot-Savart's law to calculate magnetic. So see, B is equal to, what's the formula, Riddhi?
B is equal to ILB sine theta upon R square.
I, then
LB.
DL,
IDL sine theta
then
upon R sine theta
sine theta.
upon R square.
Okay, any constant?
I is constant.
I is the current, mu naught by
Yeah.
4 pi.
All right.
Okay, this is the complete formula, mu naught by 4 pi. So
Okay.
look, mu naught by 4 pi is value we discussed. What was it?
It was I don't know if we discussed it.
We
Wait, let
discussed
me
it.
check.
Check in your notes.
Yeah, it's 10 to the power minus 7.
10 to the power minus 7. See, mu, if only mu naught you have to write, you can write it as 4 pi into 10 to the power minus 7. When it is mu naught by 4 pi, then that will be 10 to the power minus 7.
10 to the
Yes. What's the current given in the question?
10 ampere.
10 ampere. And DL?
0.001.
So I think it's better if I write it as 10 to the power
1 into
minus
10.
3.
Yeah.
So that all the powers will be solved. And what is sine 90 degree, Riddhi?
1.
1. So 4 pi has already been considered. And what is r square here?
R square. The 10 into 10. 10 square.
So that becomes 10 into 10. Yes. So 110 gets cancelled. See, what will be our final answer? This is minus 7, minus 3. This is 10 to the power minus 10. This minus goes, so 10 to the power minus 11. Okay. Now tell me the direction. This is the magnitude using Biot-Savart law. Tell me the direction of magnetic field at point P.
Okay. Outwards.
Correct. Outwards. Put your hand in the direction of current. Curl the fingers towards point P. Outwards. So see, since it is x-axis, this is y-axis. Outwards will definitely give you a positive z-axis. So your complete answer will be 10 to the power minus 11 k cap Tesla. Okay.
Okay.
All right. Please write this.
Done, mom.
Okay. Now, see, there is just in the Biot Servant law, just in case if you see, till now this question hasn't come yet. If charge is given to you, so we know current is equal to dq over dt from current electricity
Yeah.
rate of change of charge. Now, look, if this is the value of current and I write the Biot Savart law, B is equal to mu naught I dl sine theta divided by 4 pi r square, everything. Okay. And instead of this I just put this i's value. Means what's the formula of I? So I'll probably get this mu naught by 4 pi is there into, for the current, I'll write dq over dt into, this is dl sine theta divided by r square. So look, can you just tell me what is this?
Um, very, I don't know.
dl over
Velocity,
dt?
velocity.
Yes, dl over dt, it will be velocity, correct. So this is velocity. So it means now something new we will get. Current has gone and this length has gone. What are we getting? Mu naught by 4 pi will be as it is. dq
DQ.
is here. Yes, v sine theta by r square. Now AB sine theta means A cross B and
Yeah.
the dot product. So we'll get mu naught dq cross V divided by r square. That's it, a 4 pi r square. So this is also one formula you can use if you see any question based on charge and velocity. Then we have the applications of Biot-Savart's law. Yes, Riddhi, you there?
Yeah, I'm here. I'm here.
What are you writing?
I was just writing that.
I'll give you time. Don't worry.
Okay.
I'll just give you time. Just one more thing. I'll give you enough time. See, here we have the applications of Biot-Savart law. Okay, so just understand what all the things are included and not. Then we'll begin with the derivations and all, so you will understand. For straight wires, you have three kinds of wires in your syllabus. First kind of wires are the infinitely long wires. Infinitely long wires. Infinitely long wires means the ends of both the wires are extending up to infinity. They are so long. One is this. Second will be semi-infinite. Semi-infinite is infinite, half is finite. Then you have the third
Yeah.
category as finite wires. Now see, these Riddhi, you don't have the derivation of any of these. Okay, you just need to remember the formula. So a lot of derivation has been cut from this. Earlier the derivations were there, now this is not there in your board exams. And amongst these also, infinitely long wire formula you will remember, semi-infinite you will remember, you don't need to go even towards the finite wires. These are for the competitive exams in NEET and JEE. These come infinitely long wires and semi-infinitely long wires. You just have to remember the formula. That's it. So these two are there in your CBSE syllabus. And regarding the circular wires that are present, these were straight wires. Here you have three kinds of wires. First is a complete circular loop. Now in circular loop, you will have to calculate magnetic field at the center of the circle and at a point on its axis. Second is a semicircular loop. Semicircle. And third is any circular arc. Any circular arc means which is subtending any angle. It isn't fixed. It's not like your 0 degree, 180 degree or anything. This isn't fixed. So this is arc, semicircular arc. Now here, Riddhi, you have the derivations of all of these. This one, this one, this one, this one. And derivations are very similar. Up to one point we'll be doing, and the rest we will be able to write them by yourselves. And formula also you have. Okay, so this is how we'll be going about the applications. So Riddhi, now you start copying from it. Make a note point. Okay.
Okay. Please scroll. Yes, I'm done, ma'am.
All right. So see, as I discussed, let me first discuss infinitely long and semi-infinitely long wires. Okay.
Okay.
See, this is how you will have you will have infinitely long wires. This is a long wire. Sometimes you will not just get the term infinitely long. You'll have very long or even long wires are mentioned. So they are assumed to be infinite only. So when you're not able to predict anything, whether it's given as infinitely long or not, just write long wire. That will be sufficient. Now see, infinitely long wire means you have a wire. Both the edges are pointing up towards the infinity. They are getting extended up to infinity. And you have a point. Let's say this is the point P where you are calculating the magnetic field at this point. So formula, just remember the formula. How is it come? It actually comes from the main formula of the finite wire. There we put in the angles and then we get the formula for. So here the magnetic field will be mu naught I divided by 2 pi. This is the formula. Okay. And now coming to semi-infinite wire. For semi-infinite wire, look, one edge is pointing towards infinity, but the other end of the wire, it is fixed. It is not extending up to infinity. This is rigid. The end is fixed. Now the point that you are calculating is near the fixed end. Point will never be along the infinite end. So the point will always lie near the finite. So B will be equal to mu naught I divided by 4 pi A. This is the formula and you need to remember both the formula. There's no option
Okay.
here. You have to remember because see, they will be used in conjunction with other figures. You'll have a straight wire, then you'll have a semicircle, then you'll again have a straight wire and the circular arc like this. So you'll have mixed figures. So for that, if you forget any of the formula anywhere, then you'll not be able to go to the question. Okay. And see,
Okay.
once Riddhi, a question came to plot the graph between the magnetic field and the position vector for infinitely long wires and seven. So remember, the magnetic field is completely inversely proportional to the position vector. So here the graph will be, what kind of graph is this?
Parabola.
Hyperbolic. This is hype. Whenever you have two things inversely proportional, y is inversely proportional to x, or in fact x to the power n, anything. The graph will be a hyperbolic graph. It just
Okay.
depends on the power of n. If x is 1, graph will be like this. If let's say x's power is increasing, x to the power 4, 1 by x to the power 5 something, graph just becomes steeper like this. This is the difference, but
Okay.
graph's nature will always remain as hyperbolic. Okay, so let's move on to the question. But before that, you write the formula, and if there's any doubt with it, please clarify. Okay.
Okay.
Right.
Is the distance? Okay.
Yes, distance of which we say a position vector from the current element to the point of
Okay.
calculation.
Yes, ma'am. Can you scroll? Yes, ma'am.
Okay, Riddhi, let's discuss the question first, and you can write this question. In this question, 3 points are given to you: A point, B point, and C point. And it's mentioned in the question itself that what kind of wires are given. Usually, you have to identify the wires. Also, I'll share an assignment today. Two assignment I'll give. One based on just Biot-Savart laws application, which we did, one question, and one or two questions from here. Okay, if let's see what we are able to complete today. So A point is what? A is the point which is the infinitely long wire. Okay, A point is representing that your wire is infinitely long. So current flowing is 10 ampere, position vector is 2 meter, and the wire is infinite. So just basic simple usage of the formula. The magnetic field at the A point is mu naught I by, see, it's a infinite wire. So it will be 2 pi r. Now mu naught, what's the value of mu naught?
It's 10 to the power 7 into 4 pi. But then we will write it as 2 into 10 to the power 7 because there's 2
Yeah,
pi in
this
the
will be
denominator.
cancelled. Correct. So 4 pi into 10 to the power minus 7. Current is 10 ampere. This is 2 pi into this is 2. So 2 will be cancelled. And this becomes 10 to the power.
10 to
See,
the
this
power
is 1.
minus 6.
Now, direction.
Direction. Okay. So inwards. The
Direction
point
will
is.
be inwards, correct. Your palm like this, thumb is pointing, very good. Now inwards, most of the time you can write it in terms of the axis. Unit vectors you can write inwards also. You can directly
Okay.
write it in words also, INWARDS, like this inwards, that will also be fine. You can make the symbol
Okay.
of inwards into the page, anything, any direction is fine. But prefer the
Okay.
unit vectors for the combination part. Right now, this is an
Okay.
individual question, but when you have all the questions in different planes, you will have the things. One wire in the XY plane, other wire is going straight across the Y axis. So for that, unit vectors are the safest. So that's why I also write
Okay.
unit vectors. This is the answer for the first. Now see Riddhi. Yes, Riddhi, for B point, see, B point is lying on the axis of the wire. Can you see? This is
Yeah.
neither infinite nor semi-infinite. It is lying on the axis. Now, if something is lying on the axis, we take this angle as our theta, sine theta, which we consider. This is our sine theta. Here it
Yeah.
was 90 degree. That's why we didn't do anything else. Anyways, here we have the derived already solved formula. Now, Tiradi, the angle
So
that
a magnetic field will be 0
magnetic field will be zero. Reason?
because the theta is 0 degree because it's complete. It's like overlapping the
Yes.
current.
Theta is 0 degree. Okay,
Yeah.
here when we use B is equal to mu naught I dl sine 0 degree divided by 4 pi r square. So remember it as a general answer. Okay, that magnetic field at the axis will be 0. Remember it as
Okay.
a general answer because you will be using it further also. Okay, so no direction, nothing. Magnetic field is 0, story is over. Coming to C
Can
point.
in like without solving also logically we can say that because of the electricity there is a magnetic field. So since the point is on the electric field, it won't have any magnetic force, right? Or magnetic field.
See, for that, which the logic point that you're saying that magnetic field is lying on the axis, so there won't
Yeah.
be any magnetic field existing. But
Yeah.
magnetic field comes due to current.
Yeah. But it's on
current,
lying on the
it is,
current.
yes, it is
Mm.
on the axis of it. This is on the axis of it, of the wire. But it depends on what kind of wire is it. When we go by that logic part, no.
Right.
If it's a very short wire, then why won't it have a magnetic field at this point? If it is infinite, definitely point is lying on its axis. But if it's a finite wire, if you have a small wire, why can't be the magnetic field here? Current will produce a magnetic field around. Okay, but yes, you are right. It won't be there. It won't be
Okay.
there because of experiments and all. When they were done, according to Biot-Savart law, you will just have the magnetic field zero. Okay. Coming to the C point, it is infinitely a semi-infinite wire. So formula is 4 pi. Now mu naught by 4 pi directly 10 to the power minus 7. Current flowing is 10 divided by separation is 2. So 5 into 10 to the power minus 7. What's the direction, Riddhi, for the C point?
Direction. Same. It will
Same.
be inwards.
Because exactly, it's just located below. So why will it
Yeah.
deflect it, right? This is minus k cap this. You can, as I said, you can write any direction. You can make this symbol. You can write inwards. These are all fine. Okay. Where, in the board exams, all are accepted. It's just that for combination of figures, k cap and I cap, j cap, these will just help you decide. Okay. All right.
Okay.
Please write it.
Yes, sir. Ma'am, I wrote it.
Okay, look, let's discuss this question. Now you have two infinitely long wires, okay? And at the center, you need to calculate. So see, Riddhi, just treat them as vectors. You first use all your knowledge of the class 12th of magnetics chapter to get the magnitude. You use your right hand rule for the direction. Once that is done, then your physics of class 11, that part is completely over. You need to incorporate the portions that you have studied in class 11, your vectors. Now your vectors will do a part, because net magnetic field, how do you get net magnetic field? How do you get net force? How do you get a net electric field? Those are just vectors which we solve them vectorically. So here also
Yeah.
you'll have to consider them as vectors, proper vectors. Okay. So see, these are two infinitely long wires. It's not mentioned in the question. Through the diagram I'm able to identify, because infinity symbol is there. So sometimes
Yeah.
you'll just have the infinite symbol. I'll share an assignment also that will give you an idea. So look at this point P when we are calculating. This is a long infinitely wire. Now, infinite wires have the formula. Let me write down the formula separately for both of the wires. Okay. See, mu naught I by 2 pi A is the formula for this. Current is I, separation is A.
Yeah.
So mu naught I by 2 pi A. Riddhi, tell me the direction for this.
So it will be inwards
It will be, yes, inwards, right?
for the first wire.
For the first one. So I'll write it as minus k cap, so that when you add them vectorically, this will make sense. Okay, coming to B2. See, mu naught, but current is 2I.
2i.
Okay, so this time we'll put 2I divided by 2 pi A. Now, direction,
Can we not cancel the 2 and 2? Or
can we not cancel?
the 2 of I and 2 of the denominator?
Yes, yes, we will. We can
Okay.
cancel. Okay, because now these are just separate formula which can be resolved. Okay, its direction
Okay.
is.
Yeah, outwards. So
So,
K
Riddhi,
cap.
yes. So look, isn't it like at this point, one was this one. This I'm not able to draw obviously inside, but just imagine this
Yeah.
is going inwards, right? One is like this, one is like this. This is what we are getting ultimately at this point.
Yeah.
Okay. Now, two vectors in opposite direction, they have to be subtracted, even if you take just the
Yeah.
magnitude. And even if you go by the calculations, when you will add, eventually this will be subtracted because of this minus k cap. Right. So one thing should be clear, that you are subtracting. Now I didn't cancel this so that I could take common. 2 pi I can take
Okay.
common. Okay, that's right. Now the net magnetic field will be, we just have to subtract B2 minus B1. So this is mu naught 2I divided by 2 pi A. Here we have minus mu naught I by 2 pi A. And k cap is also common for both of it. Finally, the resultant will be along the z axis only. So look, if I take mu naught I by 2 pi A common, I'll be left with 2 minus 1 k cap. 2
Okay.
minus 1 is 1. So what's the final
1.
answer? Yes. Final answer will be 1 into this, that is mu naught I by 2 pi A. Magnitude, k cap for the direction, Tesla for the unit. This is how you have to answer when you have multiple. Okay.
Okay.
Then we'll come to the circular parts derivation. You write down this one. Okay. If there's anything till now you need to ask Riddhi, please ask. Okay.
Okay. So both are infinitely long wires.
Here both are infinity, because both the symbols are showing that the wires are infinity.
Okay. Yes. I have a question.
Yeah.
Uh, is it is the if we're taking after subtracting, we're just taking it as k cap? Is it because there is one minus k cap and there's one plus k cap?
See, when you have the magnetic field present like this, net magnetic field will be either along the positive z axis or negative, because
Yeah,
this is along the z axis. So k cap will
yeah.
be there. Okay. But now
Okay.
determining in which direction will it be? Will it be positive k cap or negative k cap? See, one thing is, Riddhi, when you are unaware, completely unaware, for those cases, like you will not be, mostly the cases are fine, but still you are completely unaware, you don't know which value to take, you're not able to identify, you simply add these two. How do you get the net magnetic field? Vectorically, the net magnetic field is B1 vector plus B2 vector. This is just the
Yeah.
magnitude. When you put in the magnitude, remove the vector symbols also from here. These are when you write the magnitude. So vectorically, this is what you get, right? Now see, when
Yeah.
you will add them, eventually adding will have a negative sign here, and you will automatically be left with k cap with mathematics,
Okay.
right?
Yeah.
Other than that, what you can do for your surety, B2 is mu naught 2 times I by 2 pi a. This is mu naught I by 2 pi a. At least we are able to identify B2 is greater than B1. So if two
Yeah.
vectors are there, if one force is acting 50 Newton, one is 2 Newton. So the resultant will be towards the 50 Newton. So that clearly shows
Yeah.
that the net direction will be along positive k cap. Okay.
Okay. Yes.
All right. Now let's come to three kinds of monotonous derivation we are going to do. Okay, they'll be having a similar pattern, and you'll have to write them also three times because any of them can come. And recently it is noticed that really lots of questions have come from this one, and especially that axis one which I mentioned. Axis one I'll teach you separately because that requires a lot of things and all. It's different from these, but these three have a similar pattern. So what I do,
Okay.
I take a circular arc over here. This is a circular arc. Now let's say some amount of current is flowing, which is I, throughout the circle. And right now we are finding at the center what is the magnetic field. So what is this?
Radius.
Radius. This is the radius of a circle. So what we will do, we'll choose a very small current element dl. Okay. Now remember a rule of dl for the circle. Now everything is regarding circular part, right? We'll see different rules for the direction. For finite
Yeah.
wire, straight wires we have done. One rule is that this dl will always be tangential. The direction of the current element will be taken tangential. Okay, because it's a very small part. So you will not be able to take the current when the DL was taken for a straight wire, whatever was the direction of current was taken. Now the direction of DL will always be tangential. You keep that in mind because most of the numericals will also be solved through this. Now the
Okay.
angle between DL and R is quite obvious, 90 degree.
Yeah.
Yes. Okay. Now coming to the derivation. I'll apply the Biot-Savart law. Okay. Biot-Savart law will say mu naught I dl sine theta divided by 4 pi r square. Now, since I'm just talking about this dl, I'll have to integrate it to find it for the complete circle. Yes.
Yeah.
Now, sine theta will be 90 degree. So, mu naught I dl sine 90 degree divided by 4 pi capital R. I've taken capital R. I'll take here also then capital R because here I've taken capital R. Capital R square. Now, Riddhi, sine 90 will be 1. Look, the rest of the constants can be taken out of the integral symbol.
Mm.
So can I say mu naught will be taken out? It's a constant. Current
Yeah,
will be fixed throughout the wire. DL is a variable. We cannot take that. But 4 pi r square can also be taken outside.
yeah.
Radius is also fixed. 4 pi is fixed. Integral of DL will definitely change. That we cannot take. We'll be left with this. Now, Riddhi, look here. If I add all the DLs that are present, all the DL, integral of DL means what? You're adding all the small DLs that you have. What will we get?
The circumference.
Circumference. That is 2 pi r.
Yeah.
So B is equal to mu naught I by 4 pi r square into 2 pi r. Radius will be 1, radius will cancel this, 2 pi will give a 2 here. So the formula of magnetic field is B is equal to mu naught I by 2r at the center of a circle. That is just for one circle. Let's say many
At the
circular
center.
turns are there at the center. Magnetic field
Okay.
here, you will get the magnetic field value at the center. Okay. And if multiple circles are there, n number of turns are there, so you multiply it with n times mu naught I divided by 2r, where n is the number of turns.
So for like a solenoid.
Like the solenoid, yes. Like a solenoid, but solenoid is actually a constructed device. Solenoid is a
Oh,
device. But circle,
yeah.
any circular terms, you can just turn a wire and make a circle. That's it. Solenoid is actually a
Okay.
standard device that is made. So do one thing, Riddhi,
Okay.
you write down this derivation and then I'll explain you the law for this, the right hand law. Okay.
Okay.
Riddhi, you're muted. Were you saying that you've written?
Yeah, I'm done writing it.
Okay. Till here you've done?
Yeah,
Okay. Now let's come to the rule. See, for the straight wire, those two rules are clear to you.
yeah,
For circular wire, what we'll do, whatever will be the direction of the current flow, you curl your fingers like that for of the right hand. Okay. So here, let's say this first figure. Okay. Now the current is flowing in which manner? Current is flowing clockwise like this.
clockwise.
So I'll also have to curl my fingers clockwise. Look, right hand, as if this, I have seen this figure and somebody has removed it. Now I want to explain you what was the direction of current using my fingers. So what I'll do, I'll show you like this, the current was flowing, right? Here.
Yeah,
This is clockwise. It is going clockwise. This will be the direction. So thumb is pointing inwards like this. Okay. If it is anti-clockwise, see if I do this, this is clockwise, right? This part is clockwise.
yeah,
So if I put it like this, look, isn't it anti-clockwise, going in the opposite
yeah.
direction like this? So basically your nails will just determine what is the direction. Wherever your nails are intending to point, that direction is whether you're clockwise or anti-clockwise, in whichever plane it is. So this was inwards and this will be outwards. That's how we have to follow this. Okay.
Okay. I also have seen the another type of rule for this. I think it's the bottle cap rule or
Okay, what
the
is it?
course. So like if the way you open a bottle cap, like for example, you're closing it, you're moving it clockwise, so it's going downwards. So that means it's going inwards.
Okay,
And then
but
when
then
you're
you'll be
opening
able to
it,
do
you're
it for
removing the
XY
cap.
plane.
Huh?
Then you will be only able to do it for XY plane. What if I shift this like this?
Then you'll do it like this or like this.
So no, how it is determined? Like where?
So if you're closing like this clockwise, that means you're tightening it. So then it's going downwards. So then that's the direction of magnetic
Okay,
field.
all
After.
right. Okay, if you remember that, you can use that as well.
Yeah.
But just for the notes part, write this so that just in case if you
Okay.
forget or anything, then we'll come to the question.
Yes, ma'am.
Okay, let's come to the semicircle one. So for semicircle, there will be few changes only, and I think you will be write it. You will be able to write it quickly. It's a semicircle loop. Now see, first change will be in the direction, in the diagram. Semicircle means if I have this is a semicircle. Okay, apart from this, Riddhi, can you tell me at which step will there be any change?
At the integration step.
And what should be there?
It should be pi r instead of 2 pi r.
Yes, very good. Because here you have the integral will be different. Okay, so the next derivation is now this. Once you have done with the circular one, semicircle and semicircular arc, you will be able to remember it in the class itself. You don't even need to revise it properly. Yes, this will be pi r. Pi r will cancel this. So 4r is left here. And for n turns also 4r. Okay,
Okay.
so make this figure. I'm showing this part. If you need any help, then I'll scroll it. We can write this definition. Okay,
Okay.
and then one more will discuss.
Yes, so
You're done with this?
yeah.
Okay. Now, see, last is if you have a circular arc. Circular arc means, see, in semicircle and circle, two things are fixed. That the angle which is being subtended is either 360-degree, or for a semicircle, it's just 180-degree.
180.
Okay, here when we are talking about this is slightly different, but it's similar to this. You'll be able to remember it in the class. See, circular arc means any arc. Now, this is a part of a circle, okay? And this is subtending some angle. Now, the angle that is taken in your NCRT book, it's alpha. And in the questions also, you will find that alpha term is only mentioned rather than theta or anything else. So alpha is the angle
Okay.
subtended by that. Here again, this will be the radius. And we'll again choose a small current element dl that will be perpendicular to its radius. And current will be flowing across this arc in any direction. Same rule, same right hand rule for all of these semicircle arc. You just imagine as if you have a complete circle present. Okay. Now, this is it. See, here also the change will be in the integral step. Okay, that is completely right that there will be a change in this integral step. But look, when you integrate it, basically we know integral of dl is always giving us some length L. Okay, that was the length of the semicircle, that was the length of the circle, which we called as the circumference. Now see Riddhi, here do you remember any relationship between the angle, length of an arc, radius, anything? Was there any relation from your lower classes?
Uh,
You're able to
I,
recall anything?
I'm not sure.
Okay, I'll tell you. See, whenever you have any angle, theta, it is the ratio of the length of the arc. This is valid for any arc. Length of the arc divided by the radius of the arc. Okay. So So here, can you now apply it here and tell me?
So it will be dl upon r.
DL is length. L. L means this.
Okay, so then length will be equal to theta into radius of r.
Yes, very good. So we can say length will be nothing but alpha into the radius. Here we have alpha. So you will just get, instead of dl, integral of dl, you will get alpha r this time. One radius will be cancelled. So you'll have mu naught I alpha by 4 pi. Okay.
Okay.
R square is there, 1, R is there. Okay. And n number of terms are there. So n times mu naught I alpha by 4 pi. Same rule, rest of the rules also.
Okay.
All right, now you write down this one for any circular arc. This is valid for any circular arc.
Yes, so
Okay, Riddhi, you've written till here the formula.
yeah.
Okay. So Riddhi, after today's class, what you have to do, Biot Savart law you've already done in the last class. These formula that are finally arrived. All these formula you will remember, because one more formula is left from the axis, but that I'll do in the next class because that will take a lot
Okay.
of time. Okay. But one question at least, let us practice one or two questions at least. See, this is a figure. Now we haven't done any derivation on a figure like this. We
Yeah.
didn't. This is not a figure. So what we can do, we'll try to break it into the parts that we have studied. We'll make the question convenient according to ourselves. So one is this infinitely long wire we can see. Okay, one figure is this. It's a semicircle. The second figure is this. This is the infinitely long wire third. Okay. So at the center O, here we have to calculate the magnetic field due to these. Now, these three, if broken, then they are helpful for us. We know the formula now for all these. Now, when you write down the net magnetic field,
I have a
rhetorical,
question.
yeah, say,
In the in 1 and 3, the
yes,
magnetic field on O will be 0, right?
yes, right, because the
Okay.
point is lying on that. So you will solve
Okay.
it individually only. The way we have
Okay.
done the derivations and questions, it's just you. Best part here it is If you're able to identify what all things are there, then solving the question is not at all tough. You must have done tough numericals on Coulomb's law, where large forces were given in superposition principle and all.
Yeah.
This you will find the questions are very easy to solve. So see, net magnetic field vectorically will be the sum of all. It will be the sum of B1, then you have the B2 plus B3. Now, as you rightly answered, this will be 0, this will be 0, because the point is lying on its axis.
Yeah.
And see, it's a semicircle. What will be the formula?
Mu naught I by 4 pi.
4R.
4r.
4R. Okay, direction, can you tell me?
Uh,
Any
it's like
rule you can use.
this.
Semicircle is a circular one. Straight wire
Yeah,
with
okay.
0.
So it'll be
Whatever,
inwards.
it will be inwards. Yes, this will be inwards. You can use any formula. That's what I'm saying. For the direction part, whatever you know from the
Yeah.
school, from your earlier knowledge, you can apply that. Finally, direction has to be this. Okay,
Okay.
with any method. So you're right. Now the final value will be mu naught I by 4R minus K cap, like this. Okay, please write it.
Yes, well.
One more question, let's no. Okay, one more we'll be able to.
Okay.
Okay. See, these are two concentric circles. Okay,
Yeah.
and at their centers, we need to get the net magnetic. So, see, one thing is obviously clear, clear that the net magnetic field will be the sum of both the magnetic fields. Sum means
Yeah.
vectorically sum, but when you resolve, then it depends what is the direction and all. Now, when you are confused between the figures, Riddhi, then don't write it like this in one line. What you do, write it separately. Like B1 is this, B2 is this. Then you
And
can,
then
so things
write
will
the
be
net.
clear. Yeah, when you have this thing. So see, right now I think it is fine. We'll be able to write it. Net magnetic field B1. This is the outer one. Okay.
Yeah.
It's a circle. At the center, we are calculating the magnetic field. Riddhi, tell me the magnitude.
It'll be mu naught I by 4 pi a.
2R, 2R.
2r.
Okay. But radius here is A, so 2A.
Mm.
Okay. Now, direction will be inwards. This is the same clockwise.
Yeah.
So I'm writing it as minus K cap plus. This one will be mu naught. Now, what's the current here?
It'll be 2i.
2y divided by radius is B,
2b
so 2. Direction will be
plus k cap.
plus K. It is outwards, simply plus K cap. Now here also plus K and minus K won't help very well. Here, like
Yeah.
it would have helped if these were different. This is simply inwards and outwards. One is going inwards, one is going upward. It's like one field is here, one field is here, like this. You just have two vectors which are in the opposite direction. Now see, this one is greater. Anyway, this is coming negative. Okay, with
Negative.
whichever method you solve. So here, I think it's better if we cancel
It'll be
it.
the yeah.
Yeah, if I take mu naught I by, or let me take mu naught I by 2 comma. So from here, k cap will be there definitely. From here, minus 1 by a will be left. And from here, 2 is gone, 2 by b will be left. And k cap is already common from both of these, if I put it here or put it here.
Yeah.
So this is the answer. That's it. Because values are not given. Now see, Riddhi, you can get questions where values are given. I have taken all the questions where values are not there. Means even if values were there, I just took it as I and 2i.
You
So
can
that,
simplify further.
yeah, yes. So when you'll have the values, you'll get a final answer also. Okay.
Okay.
Yes. Write it. I'll provide your assignment. Few questions I'll give you. Three questions or four. 4 questions I'll give you. Okay, Riddhi?
Okay, ma'am.